This is what we found last time. These are the two equations that we derived at the end of the last lecture. Two equations that will allow us to find psi, and from psi we will find omega, but actually what we really need is the velocity, so the three components of the velocity and pressure. And from those we'll also be able to find the stresses and the stress tensor, and from the stresses or the stress tensor we'll find the viscous force, which will help us find the Stokes law. That's very important. Now, let's consider these expressions for the velocity. We know that the velocity can be written in terms of the stream function. And now let's assume that r is very large. If r is large, well, this means that uz, the component along z, will be approximately equal to u infinity. Because if r is large, we are going very far from the sphere. And therefore, we must get something like this. And from this equation, with very large values for r, it means that uz is almost a constant. So we can integrate it. We multiply by r and integrate over r. We get that psi should behave, when r is very large, as 1/2 r squared u infinity. This is when r is very large. Let me stress that. And then, what about z? So if z is very large, for example, if we set z very large, if we go very far away, ur should be 0, right? Because the component along r should be 0. We only have a component along z. So it means that since ur is 0, when r or z are very large, so if we are very far from the sphere, if both r and z are large, but let's assume that we keep r constant and we vary z. So if z is very large, ur should be 0, and therefore this psi over dz should be 0, right? So it means that psi should be a constant in z when both z and r are very large, right? So we can see it from here, but essentially it means that also if we keep r constant and we move along z, we must get that psi is a constant with respect to z. We can try to find a solution to these two equations here. So we know the expression for psi, we know the equation for psi with respect to theta. So this is a differential equation. And in principle, you can put this part here, and you will get a differential equation for psi. So we want to find a solution for psi. And we are going to assume that psi can be written in this form, 1/2 r squared u infinity. And then we have a function f of rz here, where this function f of rz will contain some symmetry with respect to r and z. So we know that if z is very large, this function should not depend on z anymore. When r or z are very large, this function should be equal to 1, should go to 1, let's say, because psi should be of that form. And we are going to rewrite f of rz in this form. So let's write psi equal to 1/2 r squared u infinity. Then here we have 1 plus other terms which should go to 0 as r or z are very large. And the most reasonable assumption is that f of rz can be written as, in terms of powers, of 1 over the square root of r squared plus z squared, where r squared plus z squared is the distance from the origin. So in this case, we have this kind of spherical symmetry for this function, right? So I'm going to rewrite it as some coefficient a divided by the square root of r squared plus z squared. Then we have plus b divided by the square root of r squared plus z squared to the second power. So this basically gives us just the square of the distance from the origin plus c divided by, you get the idea, the square root of r squared plus z squared to the third power. And in principle you have other terms, plus dot dot dot, right? So in this way we can write also a solution. We can try to think of a solution written in this way. And we are going to assume that each of these terms, this one multiplied by that one, and this one multiplied by that one, gives us a solution. So a solution can be written in this form, r squared u infinity over 2, and then here we have some constant, and we divide by the square root of r squared plus z squared to the power alpha. So we want to see if we can find those values of alpha which will solve our differential equation for psi, written in this form. So we have to put this solution, this expression, into the differential equation for psi. So the differential equation that we want to solve is this one, where instead of omega theta, we have to think of this other differential expression. So we get in total a differential equation for psi. And this is where I'm going to make use of Matlab. So in this case, I have already written a code which takes this function, puts it inside that expression there, and gives me some results for the coefficient alpha. And let's see the code. I mean, this is just a bunch of calculations, so this will only allow us to avoid doing very nasty computations. This is the script that I've written. I have defined some symbolic variables. This is what you do in Matlab. You define the variable x, z, r, then you define theta, then you define psi, omega, and this omega here represents omega theta, which is the only non-zero component for omega. Then you have u. This u here represents u infinity, so the velocity very far from the sphere. Then we have the radius of the sphere, the component uz, the component ur. Then this grad u represents the gradient of the velocity. I have called it grad u. Then I have the pressure P, the coefficient of viscosity mu. T will be the stress tensor. We will see it later. Then we have the component u along x. So I have also calculated the expressions for the velocity in Cartesian coordinates, ux, uy, and then we have the variable x, the variable y. Then here I have n. N is the normal to the surface, so this is the normal to the sphere. We will need the normal to the sphere when we calculate the stresses, the viscous force, because we need the stress tensor and also the normal to the sphere, the normal to the surface. Then here I have tau. Tau is simply the vector of the stresses, which contains, it is related to the normal and the stress tensor. We'll see it later. Then I have some constants, A, B, C, and alpha. Alpha is exactly the alpha that you saw here. It's this alpha here, this expression, this coefficient alpha. So first thing is I defined this psi, this function psi that you can see also on the right here. So this is the expression, but you can see it more, let's say, visually on the right, and it is exactly this expression here, r squared u infinity over 2. So you get r squared u, which is u infinity, divided by 2, then you get a constant c, and then you get r divided by the square root of r squared plus z squared to the alpha. Okay, so in this case you also have r to the alpha. Let me see if I have put it there. My expression, no, so I could have also rewritten this as cr to the alpha. It's really the same. So for example, here also I could have put r, then here I could have put r squared to normalize my expressions. So it means that in this case, A, B, and C are dimensionless constants, and here I have r cubed. I mean, this is not really important. Those are just constants. R is a constant and it doesn't really matter. But yes, I can rewrite my expression like this, and then I will solve I will put this function psi into the differential equation. So I have defined omega here as simply this equation. So I have written this equation here, omega theta, equal to minus d over dr, and in this case in Matlab you have to put minus diff, which is minus the derivative with respect to this variable here, which is r, and then inside this derivative we have 1 over r times the derivative of psi with respect to r. So it's exactly this expression, this part here of the expression, and then you have minus 1 over r here times the derivative, the second derivative of psi with respect to z, and this is how you write it. You use twice the function diff. And then I have also simplified the expression for omega here, and then I have written the differential equation for omega theta, this one here, which should be equal to 0, right? And I have simply defined this part of the equation equal to some function L. Instead of 0 here, I am considering L, and I want L to be 0, right? So let me go back to the script, and you can see that this is the expression for omega. So I have calculated omega, and then I have calculated L, and finally I have rewritten L by simplifying it, and I have called the variable L in this different manner, check differential equation, which is something that should be equal to 0. And you can see that the expression is this one that I have highlighted here. You can see that if this parenthesis here, which depends only on alpha, is 0, you can see that our differential equation is satisfied, right? You can see it here. And then I have solved this algebraic equation, and I have solved it here. So I have used the function solve check differential equation, because that's the in this case it's this equation here that I want to solve with respect to alpha. So I want to find those values of alpha which will solve my equation, and the result is here. So I have found the exponents alpha which will satisfy my equation. The exponents are -2, 0, 1, and 3. And you can easily see that I have to discard the -2 coefficient, so that cannot be accepted, because if I choose the exponent -2, here my function psi will be of the form something times the square root of r squared plus z squared to the second power, because if I set alpha equal to -2, psi will be proportional to this if alpha is equal to -2. And this is not acceptable, because when r or z are very large, this will explode. So this is not acceptable. But we can choose the other three coefficients, 0, 1, and 3. So I can rewrite my expression as a sum of these terms, where alpha is equal to 0, where alpha is equal to 3, and alpha is equal to 1, not 2. The solutions are 0, 3, and 1, if you check, right? So I can rewrite my expression psi in this form. Actually, it is equal to r squared u infinity over 2. Then, if alpha is equal to 0, we see that here we just have a constant, and we know that that constant should be equal to 1, because at infinity, when r or z are very large, this is the only remaining term, and therefore we get this one. Then we get plus, and I will call this constant a, r, divided by the square root of r squared plus z squared. And then I have plus another constant that I will call b, r cubed divided by the square root of r squared plus z squared to the third power, like this. And this is indeed what I have defined here in Matlab. You can see here that I have exactly the same thing. I have r squared u infinity over 2. Of course, instead of u infinity, I just have u. And then I have 1 plus ar over the square root of r squared plus z squared. And then I have plus b r cubed divided by the square root of r squared plus z squared to the third power. Or you can just rewrite it like this, r squared plus z squared to the power 3 over 2. Right? And now what we have to do is we have to find the values for a and b. We have to find those constants, a and b, and this can be found thanks to these boundary conditions. In particular, we have already used this condition here. So when r or z are very large, we know that psi behaves like this. We already know that because this is already equal to 1. But we need to use this condition here. U of r is equal to 0 when the square root of r squared plus z squared is equal to r. In that case, we know that u should be 0. And that's the next step of the derivation here. So I have calculated omega from psi, and I have simply used the differential equation that we have, this one. Or in particular, if you want to see it here, it is this one. So we have minus the derivative with respect to r of 1 over r, derivative of psi with respect to r, minus 1 over r, d squared psi over dz squared. And it's exactly this expression here. So I have minus the derivative, which is minus diff with respect to r, of 1 over r times the derivative of psi with respect to r. And then I have minus 1 over r times the second derivative of psi with respect to z. And then I have rewritten omega, I have simplified the expression, and it can be written like this. Omega is equal to a capital R, then I have ru divided by r squared plus z squared to the power 3 over 2. And then what did I do? I have checked again the differential equation. And in this case, you can see that if I write my function psi in this manner, the differential equation is equal to 0. But we already knew that from above, actually, because those terms, each one of these terms simply satisfy the differential equation. You can see that I have rewritten psi here, and it is exactly this expression here. And then I have rewritten the omega. From omega, I have rewritten the differential equation, and then after I rewrote the differential equation, I have also rewritten uz and ur. uz and ur are simply derivatives of the function psi. So, for example, uz is equal to 1 over r times the derivative of psi with respect to r, and actually ur is minus 1 over r times the derivative of psi with respect to z here. And you can see that Matlab writes uz and ur for me here. And then I also rewrote, this is just the identity matrix that I will use later, so I don't need it here. The identity matrix will be used in the expression for the stress tensor, so I will show you later. And then I have rewritten the the component of the velocity along x, the component of the velocity along y, and the component of the velocity along z. So for example, ux is simply ur times x divided by the square root of x squared plus y squared. And this function subs will simply substitute in place of r this expression, square root of x squared plus y squared, because r is simply equal to the square root of x squared plus y squared. It is the radial distance and perpendicular to the z-axis. Then Similarly, we have uy, and you can use the formulas that we derived in the previous lecture for ux and uy. They will depend on ur and u theta, but u theta is equal to 0. So this is what you get. And then you have uz. uz is simply equal to uz, but I have substituted in place of r, I have put x squared plus y squared. Okay, and here you should see, okay, this is ux, then you get uy, and then you get uz, where sigma 1, sigma 2 are these coefficients. They are defined by Matlab. And then I can also rewrite psi. And I have to rewrite psi with the values for the constants a and b. How do I find the values for a and b? Well, now that I have the equations for ux, uy, uz, remember, I know that when I'm on the sphere, these equations here should give me 0. ux, uy, uz should be equal to 0. So for example, let's take ux. And when x squared plus y squared plus z squared is equal to r squared, this expression should be 0. So let me use my whiteboard here to show you. And okay, let me write here. So I'm considering ux, and you can see that when when x squared plus y squared plus z squared is equal to r squared, we get 3b r squared plus, and then here we have a r squared, because we have az squared plus ax squared plus y squared a, which gives me a r squared. And therefore this should be equal to 0, which means that 3b plus a is equal to 0. And then we need another equation. So the other equation that we can obtain is from uz, and there is a little bit more algebra here, but you simply have to put uz equal to 0 when x squared plus y squared plus z squared is equal to r squared. And what you will find is another condition that will allow you to find two equations and two unknowns for b and a. And the solution that you will find is this. You will find that a is equal to minus 3 over 2, whereas b will be equal to 1/2 here. Okay, so here I have simply substituted in the expression for psi the values for a and b. And let's take a look at our expression, and it is this one. So the expression for psi is exactly this one. Then I have recalculated omega here, and I don't know why it is written twice. Maybe it's because I have not put semicolon here, the semicolon. And but anyway, it is simply omega, it's written twice. And then I have calculated uz, ur with these known values for the constants. Ur is this one, and ux is this one, uy is this one, and then uz is this one, where Matlab also defines these two constants, sigma 1 and sigma 2. And then I have calculated the gradient of the pressure, because remember that the gradient of the pressure is related to the Laplacian of the velocity from Navier Stokes here, the first equation that we wrote last time. Since we have found u, we can find the Laplacian of u, so it's just a matter of calculations, and I have done that in Matlab. So you see that I have multiplied mu by the derivative of the gradient of u with respect to x. So this first term here is simply d squared u1 over dx squared. So in this case, I've calculated the gradient of the pressure on the x-axis, so that's just dp over dx. I have rewritten exactly this equation here, so I have dp dx equal to mu d squared ux dx squared plus mu d squared ux dy squared plus mu d squared ux dz squared. I have rewritten this in Matlab because now I know ux and I can calculate these derivatives, these three derivatives here. Ux derivative, the second derivative of ux with respect to x, the second derivative of ux with respect to y, the second derivative of ux with respect to z, and it's this expression here, mu times the derivative of the gradient 1, 1, and if you check this expression here, the derivative, so the gradient the gradient of u 1, 1, so this will be a matrix in this case. The gradient of the velocity is a matrix, and I have defined the matrix here. So gradient 1, 1 will be the derivative of ux with respect to x, and then the gradient of the velocity, since it is a matrix, on the first row and second column will have the derivative of ux with respect to y, and so on and so forth. This will be useful when we calculate the stresses, the stress tensor in particular, because the stress tensor contains the gradient of the velocity and also the transpose of this, but we will see it later. And therefore, I have simply calculated these derivatives here. So I have diff grad u 1, 1 with respect to x is simply the derivative of ux with respect to x twice. So it's the second derivative of ux with respect to x. Then here I have the second derivative of ux with respect to y, and here I have the second derivative of ux with respect to z. And after I calculate this gradient with respect, so in this case it is the partial derivative of the pressure with respect to x, I have to integrate that function with respect to x to find the pressure. The pressure will be simply the integral of the derivative of p with respect to x over x. So I simply have to integrate, and this is the expression that I find for the pressure here. And to check that our equations are satisfied, I have simply calculated here, that you can see here, I have calculated the gradient of the pressure. So I have the partial derivative of the pressure with respect to x, the partial derivative of the pressure with respect to y, the partial derivative with respect to z, and I have checked that this equation here is satisfied. So it is simply one line of code here where you see this is a variable check pressure formula. This variable should be 0, and you can see that indeed it is 0. And then here I have also checked that the divergence of the velocity is 0. This is just a check, and here it is indeed 0. And finally I have calculated here the stress tensor. So the stress tensor, we derived an expression for the stress tensor when we derived the Navier Stokes equations. But the stress tensor T that we called T tilde was given by minus the pressure times the identity matrix, and then here we have plus mu the gradient of the velocity, which is a matrix here because this is dui dxj if you want. So this contains two indices and it is a matrix. And then we have plus the same matrix but with the transpose here. So we have to take the transpose also because we know that the stress tensor must be symmetric. So this expression here is symmetric. And let's see if I have wrote it like that. Yes, I have minus pi, the identity matrix that I had defined previously, plus mu, gradient of u, plus the transpose of the gradient of u. And there it is. And then after I have the stress tensor, I can find the stress vector tau, which is given by the stress tensor and the stress tensor acting on the normal to the surface, where the normal written in Cartesian coordinates, since we are considering a sphere, it's simply x divided by the square root of x squared plus y squared plus z squared, and then I have y divided by this same square root, which I can simply call rho, and then I have z divided by rho, like that. And I have defined n in this manner. So n is equal to n1, n2, and 3, where n1, the component along x, is x divided by the square root of x squared plus y squared plus z squared, and similarly for y and z, y divided by square root of x squared plus y squared plus z squared, and then I have z divided by the square root of x squared plus y squared plus z squared. And then I have defined tau, which is the stress vector, and I multiply the stress tensor by n, and in this case I simplify the expression with this number of steps. This means that I let Matlab do 150 steps to simplify the expression, just for the sake of convenience. Sometimes, since the expressions are complicated, Matlab might not be able to simplify the expression with just one step. So I have increased the number of steps, but just for the sake of convenience. And then what did I do here? In this case, I'm preparing to integrate tau, because now that I have tau, in order to find the force, the viscous force, I have to integrate tau over the surface. So this will be the force, the viscous force, let me call it Fe, which is equal to the integral over the surface of the sphere, tau. And I will do this in spherical coordinates. So if I use spherical coordinates, I will substitute for x, I will substitute r cosine theta sine phi, whereas for y, I will substitute r sine theta sine phi, and for z, I will substitute r cosine phi, where phi is a variable which ranges from 0 to pi, whereas theta is a variable which ranges from 0 to 2 pi. So theta is the variable on the xy plane, whereas phi is the variable, so it's the angle with respect to the z-axis. So if I have a polar system, phi is the angle with respect to the z-axis of a certain vector here. Okay, let me draw the x-axis, the y-axis, and then here we have some vector which has a projection on the xy plane of this kind. The angle between this vector and the z-axis is phi, and the angle between the projection and the x-axis is theta. Theta can go from 0 to 2 pi for a sphere, whereas phi can go from 0 to pi, right? And then we have to integrate over phi from 0 to pi and over theta from 0 to 2 pi. So I was getting ready to to write tau in polar coordinates, spherical coordinates, I should say here. And so I have called the vector tau spherical. You can see that I have renamed tau as tau spherical because I have rewritten it in spherical coordinates. And then I do one first integration, this one here. I integrate over phi from 0 to pi here. And I integrate the function tau spherical, but I also have to remember that I have to multiply by the Jacobian of my integral, which is r squared sine phi. So I do this integral first, and then I finally integrate over theta from 0 to 2 pi. And lo and behold, this is what I get. The result for the viscous force is here. Thanks to Matlab, I didn't do any calculation, and that's very useful because you can make mistakes while doing all these calculations. So I have Fv, the viscous force, is equal to this vector here, 0, 0, and then here I have 6 pi mu r u infinity, where, as I said, u is equal to u infinity. And this is exactly Stokes' law. So it's incredible to see how all these steps will take us from Navier Stokes equations to this magnificent law, very useful law in hydrodynamics, very famous formula derived by Stokes in the 19th century, I think, so in the 1800s, of course. I don't remember the year in which Stokes was able to derive this formula, but you can see that it is quite painful to derive this formula from Navier Stokes equations. So that's the most, let's say, rigorous way to derive this formula. Then there are other ways, of course, which are more heuristic, let's say, and they are described on Wikipedia. If you go and check Stokes' law, it is mentioned I mean, Wikipedia also mentions the derivation that we went through in these two lectures. You can see the formula for psi here, and then, I mean, Wikipedia describes how to find the solution, but you don't see all the steps. And I have shown you all the steps to find Stokes' law, and Wikipedia also gives an interesting heuristic proof, and you can read it here, but this is not really a rigorous proof, so it's just heuristic. And that's basically it. So I wanted to find this magnificent law, which is known as Stokes' law, and it is not so easy to find these derivations online. So if you manage to follow the steps, I think it might also be very useful to give you more intuition about this. So thank you for watching, and see you next time.